Okay, so that's actually a picture that we took of Clyde's spot. We were fortuitously already flying over that just 2 days after it was discovered by the amateur Clyde, and we got a good shot of it. But let's go to the next slide. Okay, so the status is everything's healthy on Juno. We, of course, launched in 2011, arrived in 2016. We're currently scheduled to have the prime mission end next summer, and that comprises 34 orbits, all of them 53 days long. The extended mission proposals, and I talked a little bit about this the last OPAG, are due September 30th. They were delayed because of the COVID stuff. And we expect a decision in December. And the plans are far enough along that I can talk about them and show what we plan to do. And I'm kind of excited because I think it's a really good thing for the OPAG community. So we add quite a few orbits in the extended mission. It goes through 2025. And what part of the reason is that the orbits get smaller than 53 days. So we're able to actually pack more of them in by the time September 2025 comes along. Next slide. And then here's our payload, just to remind you that we have quite an extensive payload that deals from everything from the Doppler gravity experiment, the magnetometers, quite a few cameras, some of them tied to the magnetometer star cameras. We have a regular main star camera that we use for science as well, the MWR, which is the microwave sounding charged particles, both energetic and low energy plasma waves all make up the fields and particles, an ultraviolet and an infrared spectral imagers. And then Juno Cam, which we are using a lot for science, but it was originally intended to be an outreach camera. And so we have quite a few instruments on here that I list that we're planning to use for science in the extended mission, that we're really engineering subsystems in the primary mission. Okay, next slide. And one of the exciting things about our mission in the extended mission is we're going to go and visit the satellites in the rings. I'll show you how that works, but it really becomes a full system explorer, not as focused as the prime mission was. And so it feeds potentially a more diverse OPAG community, because the satellites, geologists, ring people will all get data that I think is very interesting and unique. Of course, the final selection, I should keep reminding you that this is a proposal that still has to get reviewed and decided upon, and it may be limited by the available budget. So what I'm going to describe is everything that we think is possible to do in the mission. Okay, next slide. Because it's branches out, we address some discoveries that we made in the prime mission, such as the whole complexity of the northern hemisphere and the polar cyclones, and the fact that some of the magnetic features like the great blue spot appear to be shearing from the deep winds. We went out to discover a core, whether there was a compact core inside of Jupiter or not. We were surprised because it was a large dilute core. But we also get these new targets associated with going through the Europa torus, Io Europa torus, I should say, and I'll show you a map. We really dissect that in a nice way. And we have multiple flybys of Io Europa and Ganymede. And then we do a very good detailed characterization of the ring. So a lot of these things are new, and the stuff on Io and Europa and Ganymede are complementary and actually build and help Clipper as well as JUICE and the potential Io explorer that's being studied now. Okay, next slide. I'm going to go kind of quick at a high level because I have a lot of slides here. So the way it works is our perijove, each orbit moves northern. So you see the blue, I should say the gray trajectory is our very first perijove, where the perijove, the first orbit, perijove 1, where the perijove was very close to the planet, but also very near the equator. And because of Jupiter's asymmetric gravity field, we slowly migrate, and the perijoves move, the line of apsides migrates north. And so By the time we end the primary mission, which is PJ34, you're on the blue line. So you've moved from about 4 degrees north to a 28-degree north perijove. And by the time you're done at the extended mission, you've moved it even further north. So this gives us close proximity to the northern parts of Jupiter, which is a new kind of frontier. We've seen a lot of activity there, and so we'll be able to explore it very close up, whereas in the primary mission, we were restricted to the lower latitudes. We also, I point out that the altitude above the pole, which is important for studying the aurora, really shrinks quite a bit in the extended mission. And one of the puzzles we have is that we've seen polar emission coming from in the aurora that doesn't match the particle precipitation, implying that the acceleration mechanisms may be going below the spacecraft. And so we'll get a chance to really test that out and explore much closer. Okay, I'm going to keep going. Next slide. So this tells you a little bit more about how the orbits change. So the gray ones are the primary mission, and you're moving inbound, right? And so you come in from the top and then go out the bottom on the bottom right there. And the gray ones, you know, basically just touched to Ganymede. That's the crossover between the prime mission and the extended mission. And so because of the movement of this perijove, that's why the satellites get into view for us, and allows close flybys. So you can see that the extended mission, which starts in different phases of the different shades of blue and purple, is we go from Ganymede into Europa by the time we get to PJ45, and then eventually get to Io. And all the time we're getting closer and closer to the rings on the inbound portion, and on the outbound portion we're inside the rings looking out. And you can see some of the data from the gray. We've already gotten some in situ data using our WAVES instrument, but when we're in these blue and purple phases, we're really going to be able to look at the rings in a much better way with remote sensing as well as the in situ measurements. So we're going to be able to do a good job on rings, almost all aspects of them, the halo, the main ring, the gossamer rings, as well as the satellites. Okay, so next slide. This is just to give you a feel for the trajectory. So here's a side view of the trajectory. And you can see that as the extended missions are in the same color blues and purples that I showed before. And you can see we're moving further and further into the southern regions of the magnetosphere. And in fact, we'll be able to go in and look at the southern magnetopause, something that's never really been seen before. So it's exciting. Okay, next slide. Now I'm going to get in. I'm sorry for a little bit of fuzziness on this. It was a PDF. But on the left-hand side, you see some images that not taken by us necessarily, but images of the rings, which are there's very few images and science been done on Jupiter's rings, but you can see some clumpiness in there. So we'll have a much better chance at really characterizing that by mapping out the rings with our Juno cam and the stellar reference unit, which sees very low light in a very good way, as well as all our stellar cameras, the ASC that's tied to the magnetometer. And on the right-hand side, you see the close-ups of that view on the outbound port, and the colored blue that has this, that's actually in situ data from our WAVES experiment, which detects impacts from dust. And so you can see in the purple that we're gonna slowly move that orbit right into the halo. And so it'll be very interesting for people that study rings. Next thing, okay, so this is a map looking down on the pole of Jupiter, and the colored part is a map from our infrared camera called JURM, where you can see some of the polar cyclones right at the innermost circle, which is sitting at about 85 degrees latitude. And then the outline of the map, the thing that kind of looks a little bit like a fish or something, that's actually the map that we'll be able to make with the microwave experiment during the extended mission. And so because of the way we spin, normally the microwave looks at very thin strips, but when you start going over the poles, it actually makes a three-dimensional map that are and we have 6 frequencies. And so we're making slices at different depths. And so we'll be able to search the depths of the roots of these storms and really understand the Jovian polar atmosphere, which is a big puzzle. How do you create these these polar cyclones. We'll be able to monitor them with the infrared and the visible cameras, but we'll also be able to look underneath to see what's underneath there. And each one of these, this is just a few examples of the maps. We'll actually make more than what I'm even showing here. And sometimes we'll be able to go over the same cyclone at different times. Each one of these is about a month or 40 days apart. Next slide. And then this has to do with the dilute core. And so one of the big surprises was that Jupiter did not have a compact core that we were expecting, or no core, but it had this large dilute core, which is really critical in understanding Jupiter's formation and evolution. The theorists are still struggling to catch up with this discovery. We'll be able to characterize that dilute core in the extended mission in a much bigger way than we can do in the primary mission, mainly because we have more orbits. And more orbits allow us to look at the tidal responses that Jupiter's gravity field has. We'll measure the global water abundance. Of course, we've seen the water and the ammonia appear to vary quite a bit with latitude. So to understand the global water, we really need to measure it up at the poles. It may be different up there. The moment of inertia, the zonal fields, and the tesseract harmonics can all help us understand the characterization of this fuzzy core. Next slide. And then the magnetic field. So this is a magnetic, the top one is a magnetic field map after just 9 orbits. And then after 24 orbits, you can see, you start to see much higher resolution. So after the extended mission, we'll really map out, you see the much more complex features, small features up in the northern hemisphere. Will be not only closer to that because of the migration of the perijove, but we'll get more orbits, and so we'll understand this. And one of the things that we're struggling to understand, it was a big discovery, was you see this great blue spot in the sort of the middle right part of that map. And then as you got more resolution, you realize that it's shearing at the top and bottom. Those are because of the deep winds. The zonal jets are moving in different directions, and they're affecting the magnetic field. So this is a big discovery. And in the, let me go to the next slide, we'll actually get more orbits focused right on that great blue spot. This just shows 24 orbits, but we'll actually be able to get 5 or 6 orbits that are just timed so that they dissect that whole great blue spot and understand how that shearing is going on. And one of the discoveries that we've made is that it's not enough to just study the interior, the deep atmosphere, and the magnetic field separately, like we've been doing with Voyager and Galileo, Cassini. Even Juno started off that way. There's a coupling going on. The deep interior and the deep atmosphere are affecting each other and are coupled and need to be studied in an interdisciplinary fashion. And the magnetic field is playing a big role of even how the atmosphere probably looks at the deep levels that we see with MWR. So we'll be able to, that's one of the investigations we'll go through. Let me go to the next one. I'm going to run out of time here. So this is all the occultations. The dotted lines are occultations that we're going to do to understand the upper atmosphere. There's quite a few of them. Next slide. This is the torus, so you can see we go through the torus in a huge way. We'll do the best job, and this is important for Clipper and Juice as well. Next slide. I'm just going to keep going faster. So on the satellites, which I know you're all interested in, we go by Ganymede, Europa, and Io, and we do surface composition maps of Ganymede, space weathering, the magnetospheric interaction. On Europa, we use MWR to actually characterize the thickness of the ice shell. We can do a plume search, we make maps, and Io will look at the magma ocean and map out the polar volcanoes and the SO2 maps, as well as the magnetospheric interaction. And of course, the semi-major axis that I know Alfred is interested in and has pointed out. Next slide. These are the actual satellite flybys, roughly by year. And you can see that there's a very close one at Europa at 320. Most of them are in the tens of thousands of kilometers. And then there's 2 close flybys of Io to understand K2 and look for the global ocean, magma ocean. Next slide. Okay, so we're gonna, there's on the right, you see a map of Ganymede's North Pole from our infrared. We'll be able to do roughly 50% of the surface at a resolution that's about double what you see here. We'll look at the role of radioelectric processes that are hitting and changing the weathering of the surface. And we'll look for changes since Voyager and Galileo. Next slide. Europa, here's a map that we'll do from the microwave instrument. So this is an example of beams. We'll actually get about 2 to 4 times better resolution than this, partly from super resolution, and also we have some channels are higher frequency. But we'll go across Europa, and you see these stripes. That's because we're spinning twice a minute. So each time we lay a track down, and we'll actually, our microwave, because it goes 1 to 50 centimeters, we're very good at looking at the shallow first 10 kilometers. So we'll see where the ice is thin and where it's thick. And we'll also be able to see where there's subsurface liquid, because there's a very easy, simple spectral signature in the microwave when you see something like that. So this is a really important experiment that I think can help CLIPPR, as well as do something that CLIPPR's reason, of course, goes at much longer wavelengths. And so this complements that. Next one. From here, we'll also map out the water ice. And this, we'll get about 10 kilometer, 1 to 2 kilometer resolution. Oh, I've got my slides out of order. I'm sorry. We're mapping about 40% of the surface at 10 kilometers here. And you look at the surface sputtering. Next slide. This is the one I thought was I was talking to, sorry. So this is the surface changes. We're gonna do a plume search. So we have about 1 to 2 kilometer resolution. With Juno Cam and the Stellar Reference Unit, we can actually look at high phase forward scattering, something that's hard to do. So we'll be able to make a very sensitive search for plumes. Whether they're there on the few flybys that we have to be able to look, I don't know, but we'll also, in the close flyby, look at the fields and particles, which will tell us quite a bit about how things are changing on the surface and what's being lost. And
Scott, can you tie it up in like a minute?
Next slide, please. And then this is the last slide. And so this is the IO one. So you see on the right here, we looked at IO with the infrared, the SRU, and the Juno Cam, and we discovered plumes that were coming up out. You can see in the middle Juno Cam image that plume is actually over across the terminator. And then we were able to map that to the infrared and the SRU plumes. And so we'll be able to use that technique not only at IO to map out the polar volcanoes, but that same idea will help us look for plumes on Europa. And then the bottom one is the magma ocean investigation. The bottom left is just a model of whether there's a global ocean on one side, the right side, or some other kind of technique which is providing the mechanism for the volcanoes. I think that's all my slides.